Hello, we are going to look at 3 questions. These are some questions of interest that some of us have asked in regards, and they're going to work through them. So question 15 of the 2008 exam. We've got 2 forces P and Q acting on a body. P acts in the direction of I with magnitude 1 Newton, and Q acts in the direction of I plus root 3j with magnitude of 4 newtons. Now, the magnitude of the total force acting on the body in newtons is. So, what we have here are 2 descriptions about vectors, but we haven't actually been told what those actual vectors are. So the first thing we have to do, use the information of size and direction, and we must state what each vector is, P and Q. Okay, so that's the first step. Once we work out what P and Q is, then we can put them together to work out the total force. So a vector is a magnitude multiplied by a direction. Okay, now the magnitude is the modulus, the direction is the unit vector. Okay, so just by drawing on the information in the question, we're going to come up with 2 vectors P and Q by using the modulus, the magnitude of the vector, and coming up with a unit vector for its direction. So P is 1 order of magnitude, 1 Newton of magnitude in the I direction. There it is. So it's 1 times I. Okay, so P is easy. Alright, but now Q. Q has 2 parts. Q has there's its magnitude and direction. Now the magnitude is, we're told, of 4 newtons. Okay, there it is, a magnitude of 4 newtons. Now the direction of Q is this vector. Okay, now that isn't the Q hat. Okay, that is the vector that Q hat is in the same direction of. So from that, we're going to form a unit vector of that vector. Alright, and this will be the same as Q hat. So you take the vector and you divide by the modulus. There it is. And that now is Q hat, and that is the direction of vector Q. Alright, so your total force now is P plus Q. So we take our sum of our 2 parts. Okay. Now here we have 4 times the unit vector of Q, and we expand to get our 3i plus 2 root 3j, which is and now the total force as a vector. Now the question is, what is the magnitude of it? So the square root of the I and the j component, we get root 21, which is d. Everybody understand? Alright. Now this next question, question 17, P, Q and R are 3 collinear, there's that interesting word there, collinear points with position vectors P, Q and R respectively, where Q lies between P and R. Now if the modulus of Q to R is half of the modulus of P to Q, then R is equal to. Alright, so to make sense of this, it's good to first, we need to know what collinear means. Collinear means points along the same line. Okay, they all points that are points on one line. Okay, so something like this. P, Q and R, points along a line. They're all collinear. Now, let's say relative to the origin, somewhere over here. This is an arbitrary position. The origin could be anywhere. It could be over here, it could be over here, it could be down here. Alright, could be anywhere. So, relative to the origin, we've got our 3 vectors, P, Q, and R. And by doing that, we can we can do some vector addition to come up with equivalence for what is vectors QR and what is vectors PQ and what is vector P to R as well. So QR, going from Q to R, that's minus Q plus R. whereas a P to Q, that's a minus P plus Q. Now, just considering the moduluses of each, we're doing that. Okay, now, just pause. I don't know what Q and P are, and I don't know what vector R is, or Q is, so to be able to evaluate this can't be done. Okay, so we got to approach it a slightly different way. The object is to determine what vector R is. So I can identify that using the fact as well we're going to draw on. I can identify that R going from O to R, well, that's the same as going from O to P, so running along vector P, and then from P over to R. So we get this, R equals P plus PR, the vector PR. Now PR is the same as from P to R, that's the same as going from P to Q, and then Q to R. Okay, but Q, because they're all in the same direction, they all have the same unit vector, okay, and the only thing that's different about Q to R and P to Q is this expression, okay, in referring to the size. And so because the unit vectors are the same, they're collinear, we can draw on the vector Q to R is just half of P to Q. Now, we've got one vector here of P to Q plus a half of P to Q, so that's 3 halves altogether of P to Q. Now, P to Q is what we worked out before, that's a negative P plus a Q. So using that, there it is. And by expanding and collecting terms, I get that, which is option A. Okay. And then there's this question, which is from 2013 exam. Okay, now this one is of question 5, part C. Now this is the second part. This is a kinematics type question. Okay, it's quite interesting because it speaks about a ramp, an inclined plane, and moving on a ramp. But this whole thing about moving up an inclined plane is actually a bit of a distractor, because the real problem is a projectile motion problem. What happens when the skier here leaves the edge of the ramp and flies up and comes back down? Alright, let's go through it. So the water skier performs a jump from top of a 10-meter long ramp, which is an incline at 30 degrees to the horizontal. To do this, the speedboat travels besides the ramp and keeps the water skier's speed at 15 meters per second directly up the ramp. So 15 meters per second is running up this direction. That's 15 meters per second. Okay? Until the water skier reaches the top. So on the point of launch, he's traveling up in this diagonal direction 15 meters per second. Okay. Now we have then the speedboat slows so that the tow rope slackens and remains slack after water skiers leaves the top of the ramp. In other words, there's no tension. Okay, that means there's no other force acting on the skier other than gravity. Assuming that negligible air resistance describes a situation of no other forces, then only subject to the force of gravity. There we go. So that means if gravity is the only force there, then we've got going down at gravity of 9.8 meters per second. It's a constant acceleration problem. Okay? Okay, now find the time it takes for the water skier to hit the water after leaving the top of the ramp. Give your answer in seconds, correct in nearest 100th second. So from here, what's the time it takes for him to go up and down? Now, that is in fact not a straight line kinematics problem. That's a two-dimensional problem. But if we break down our two-dimensional problem into vertical motion, an horizontal motion, then we've got a component there that is straight line, linear, a kinematics problem. Now the best one to consider is consider it a vertical problem only. Okay? So essentially that's the motion going up and coming straight down. Imagine a vertical velocity up and then down again, past its point of origin and below the point of origin. So it's got a displacement that is below, going down. It's like a negative displacement. So the first things we have to work out is some vertical displacement. Well, it's 10 meters as this is a right angle triangle problem. We've got 10 meters of hypotenuse. The vertical displacement here, which is this side of the ramp of the triangle, it's our sine rule, so 5 meters. And what about the initial velocity? Well, initial velocity on a diagonal like this, that's 15, and it's on an angle of 30 degrees, so the sine component of 30 degrees gives you 15 over 2, or 17.5. Okay, now going up and coming back down has a total negative displacement of 5 meters. So we use that all together. S equals ut plus half at squared. We put in our values and we solve for t. And we will get 2.03 seconds. And since time is greater than 0, this one is the correct value for the problem. And there we have it. I hope that's not too difficult, and I hope it's helpful and you've learned something. Okay, all the best.